and thanks for the invitation. It's an honor for me to speak here. So I suppose I could have written this before. Exotic. I don't know if I included type in the title, but I should have. Exotic type contact structures on R 2n-1. And I'll be describing work with, this will take me a while, François-Simon Fauteux-Chapleau. So I want to tell you about this theorem of ours. Okay, you can guess what it's going to be. There exist exotic type contact structures on n-1. In fact, infinitely many. n-1 for all n greater than 2. So starting in R5. And so I'll assume some basic familiarity with contact geometry, contact structures and whatnot. But I'm very happy to answer any questions if anyone wants to ask about anything at all. So let me begin with some remarks about this thing. First is that it fails in the case that I've excluded. N equals 2, proven some time ago by Ashberg. Classified contact structures on R3, and there's only one type 1. Okay, second, as I mentioned, we get infinitely many of them, but it wasn't known that there's one exotic contact structure. So exotic meaning not isomorphic to the standard one. However, I should mention that this much has, at least in the case where the dimension is 1 mod 4, has since been obtained independently from us. Since proven independently by Ulrich in the case 2n-1 equals 1 mod 4, using very different methods from the ones that I'll tell you about, and very nice ones. He concludes the result from a non-squeezing property for balls in exotic contact spheres. But I won't say anything more about that. Third, a comment on the place of the word tight in the theorem. If I hadn't written tight, that was already known that there's an exotic. So exotic namely over twisted context structures were already known to exist. And of course, for those who are familiar with this, much more than that is known about over twisted context structures, namely they're completely classified. So the situation is, let's say for closed M. Okay, I'm just recalling the H principle for over twisted context structures. The situation is that over twisted context structures of isomorphism are in bijection with so-called almost context structures or formal context structures. Up to homotopy. And this is the case for closed manifolds. For open manifolds, like Rn, you at least get an inclusion this way. So in particular, this is a purely topological invariant. Therefore, on Rn, there's a unique one. So
so is it known that there's a like are there potentially more over twisted ones? Is that
you can so the image is precisely what's called over twisted at infinity. Yeah, by the way, please let me know if I'm writing too small. So when you have over twisted context structures on open manifold, you can look at the ones which remain over twisted outside of any compact set, and then the ones that are tight at infinity but over twisted on a compact set. And yeah, so you get isomorphism to the over twisted infinity ones. And then for the other ones, it turns out in this, when your manifold is obtained by removing some number of points, finite number of points. So here it's obtained from the sphere like that, then the over twisted but tight at infinity ones turn out to correspond to the almost context structures on the closed manifold from which it was obtained. So that's the full situation. Okay, some more. Oh, so this is, I should mention, this is called the H principle for twisted manifolds, and it's the theorem of. Okay, I'm going to write Eliashberg several more times, so perhaps allow me to write E. From 89. So that was in the case of three-dimensional manifolds, which was the only context in which tight was defined at the time. Later, Borman in 2015, Eliashberg and Murphy extended the notion of over twisted and tight to higher dimensions, and at the same time proved the same H principle. Okay, so that's why we look at tight ones. All right, just two more comments. Maybe I'll just mention the analogous results for spheres. Okay, so first of all, S3, just like R3, has just one tight context structure. I always mean up to isomorphism. That's also theorem of Yasha, apparently from 92. And then for the spheres in dimension 3 mod 4, they have infinitely many tight context structures. And this is a old theorem of Fauteux in 76. He showed there's a tight context structure in every homotopy class of almost complex structures, and there are infinitely many of those. In 114, it's a later theorem of also has infinitely many. This is a theorem of Stolovsky from 99, and what I'm going to describe is closely related to what Stolovsky did, so I'll be returning to that. Just one more final comment before I start describing that is another word about tight and over twisted, because I haven't actually said anything about what it means, which I will continue not to do, but for anyone who may not have seen it, the things to keep in mind, or all you really need to know for this context, is first of all the thing I wrote over there, H principle for over twisted context structures, which fails. That's what makes it interesting, which fails for tight context structures. So in a given homotopy class of almost complex structures, you never know what's going to happen. There might be no tight context structures, there might be one, there might be many. And in terms of recognizing tightness, the main criterion is that any symplectically fillable contact manifold, so a contact manifold that arises as a contact boundary of a symplectic manifold, is tight. Or more generally, also open subsets of tight manifolds are tight. So also any open subset of a symplectically fillable contact manifold. So in particular, all of these results on existence of tight contact structures, in each case, you actually get a fillable contact structure. That's how you know it's tight. All right. In the case of Rn, it's not that it itself is fillable, but an open subset of a sphere which is fillable. Any questions about those things? Okay, so let me say a little bit about what Stolovsky did. So he proves for the following manifolds, so I'll call it M sub P. M is for manifold. This is the intersection of a 4m+3 sphere. So intersection of a sphere with the zero locus of a complex polynomial with a singularity at the origin. These are quite famous objects. They come up in the study of exotic spheres. Milner has a well-known book about them. So this is a subset of C 2m+2, as it turns out. Here, there's a condition that P equals plus or minus 1 mod 8. I'll just hide it in the corner here because it doesn't really matter for us. So these are called Princeton spheres. And it's a theorem of Princeton that it is in fact diffeomorphic to a sphere. So Princeton, he classified exactly which manifolds arising this way are smooth spheres and which ones are exotic spheres, which some of them are. And the point is, even the ones that are smoothly standard can still be exotic contactly. So sorry, still in the middle of the sentence. He proves for NP that the contact homology is non-trivial. So contact homology is an invariant of a closed contact manifold, which I'm also generally assuming people are familiar with. Not isomorphic. Thank you.
Which contact homology? Like, so which is like cylindrical? Like, is it like augmented, like which?
Contact homology algebra.
Just the DG. Okay, so the contact DG.
We proved it for cylindrical.
What's up?
Proved it for cylindrical.
Yeah, that's what I was. That's
cylindrical.
why I asked for the. I think he proved it for cylindrical.
Oh, okay.
Right? Maybe it's.
It says the invariance for cylindrical contact homology doesn't exist.
Yeah.
So you have to go through.
Yeah.
Yeah, sorry. Okay, yeah, maybe you read that he proved it for cylindrical.
Yeah, but
we're only going to prove the corresponding thing.
yeah, and I think they're also like dynamically convex or something like that, right? So there's no different. Is that what you were saying? There's no differentials.
Yeah.
Yeah. Thank you.
Oh yeah, so this is it. Anyway, this is the famous result. It was one of the first applications of contact homology. It appears, it's referenced in the original paper about symplectic field theory and everything. Oh, maybe just one more, sorry, just one more kind of historical citation, which is that these things, they have, it's not completely obvious how to put a contact structure on them. This is done by Lutz Meckert, 77. So that's when I talk about this as a contact manifold, comes from them. I mean, it's given by some very explicit contact form.
Can I ask a question about that?
Sure.
It's just like you perturb that thing to make a Stein filling, and then it's like the contact filling, the contact form on that. Right?
Yeah, that's true. Yeah.
So, yeah.
Exactly. Yeah. What you said. Okay, so analogously, we prove that. Yeah. So maybe. Okay. So maybe I should have used a different notation. But here I certainly mean contact homology algebra. That when you take the exotic Friese-Korn manifold, I mean the exotic contact sphere, and remove a point, then you get certainly smoothly you get Rn, and the claim is that it is exotic. And there's a similar thing that's done. In the case for m plus 3, you use a slightly different polynomial and get a corresponding result. So so there are two steps involved here. One is the computation of this. Which it quite closely follows what Ustawowski does. But and maybe I'll have some time to describe the computation at the end, although I suspect that I won't. But more fundamentally, step 0 is to define this invariant at all. And the reason it needs defining is because we're considering it for not for V closed where contact homology is normally defined, but for V open, and specifically we'll be doing it for so-called convex open contact manifolds, which is, I think, what I'll tell you about next. Okay, so that's the main thing I want to tell you about. How so in a sense, our main result is the extension of contact homology to this case of convex open manifolds. That's what I'd like to tell you about. Any questions? Okay, so let me recall what the story is with convex contact manifolds. So this is a notion due to Ashberg and Gromov, and then further investigated by Giroux, 91. So a hypersurface sigma and V in a contact manifold. So I'll write V xi for the contact structure, and I'll always be assuming that contact manifolds are co-orientable, although for this definition it's not needed. So a hypersurface is convex if it admits transverse contact vector field. Just transverse. Here, contact vector field means one which generates flow by contactomorphisms, or more explicitly, you could say that.
It was a little hard to see, just FYI.
This color?
I'm
Right.
my eyes are. That's good, yeah.
So just this condition. So this is to be compared with a contact type hypersurface in a symplectic manifold. Okay, next, given a compact contact manifold, with a convex boundary, the boundary is a hypersurface, you can ask whether it's convex. You can attach a infinite n, just as you do with Liouville manifolds. So we have collar, open neighborhood of sigma, which looks like epsilon 0 cross sigma, and form this completion B hat bar union along this open neighborhood with the infinite interval. And then we say that but by a convex open contact manifold, I mean one of this kind. Convex open manifold if V is isomorphic to V hat for some V bar as well. So equivalently, without making reference to this manifold with boundary in the completion construction, we can say directly what we want. Namely, there should be a complete vector field, contact vector field, X on V, and a proper function, proper smooth function T to R with say GT evaluated on X is outside of the convex set. So the picture will always be having in mind of a convex manifold. This, you have this T coordinate on it, and then after you go sufficiently far out, you have this hypersurface sigma, which is convex, and the end is isomorphic to sigma times an integral like this. Okay, I'll call this part of the manifold op infinity, neighborhood of infinity. So let's see. Let me just fill in this picture a little more. So here's T0, sufficiently large. This sigma is T equals T0, and it's a convex hypersurface. Okay, and we call such a pair X and T a convex structure. Okay, and the main example for our purpose is, of course, we use Rn, R2n minus 1. Alpha is the standard contact structure, standard contact form. And we can take X, for example, to be this vector field. So almost just that outward pointing radial vector field with a factor of 2 in front of the TZ. And this is a complete contact vector. And it's transverse, for example, to the unit sphere. So then you can take T to be 1 on the unit sphere, and then determined by this condition. Okay, so that presents R2n minus 1 as a convex manifold. And that's the only one I'll be worrying about, but there are many other examples, most notably by recent work of Honda and Huang. Arbitrary hypersurface in a contact manifold will be closely approximated by a convex one. So in literally any contact manifold, you can find tons of convex manifolds.
But also, so you can just delete a point from anything and then it's convex near that point. Is that?
Yeah, that's also,
with the standard kind of structured infinity, right?
Yeah.
It looks the same. Okay.
yeah, absolutely. Yeah, that's another good source. Okay, so our task is then to define this invariant for the admitting a convex structure xt. But of course, it's important that it be independent of the chosen convex structure. Independent of isomorphism. That's the only way we'll be able to conclude from computing it that that our contact structure on Rn is really different from the standard one. One remark about this is that half of this might be done in a certain sense. Calling it's pronounced Gini on the hedgings from 10. They define a version, they call it sutured contact homology for compact with convex boundary. But the way they set things up, the definition depends on the boundary and on the convex structure, at least a priori. So our improvement is then to get something which is independent of the convex. All right, what's next? Oh yeah, yes.
Do you know if your version of contact homology is the same as their version?
I assume it is, but I haven't. Okay, let me briefly recall the setup for contact homology. Which, yeah, like I said, I'm assuming or hoping we'll already know about it, especially because otherwise it would take me forever to spell it out. So I'll omit basically most of the details, but again, you ask me questions. So you have a cooriented contact manifold and a fixed contact form on it. Then we have the rate vector field. And then we consider this algebra, the contact chains algebra. Which is the free commutative Q algebra generated by the rate orbits. And one has to make various qualifications. So first of all, one needs to throw out certain rate orbits, all the bad ones. And then you also need to consider a parity on the good rate orbits, which makes the algebra Z mod 2 graded. But I'm not going to say anything more about these things. And we'll also want to assume that alpha is non-degenerate in the usual sense. So one sets up a algebra like that. Then we define a differential on it, about which again I'll say very little. So first we fix a D alpha compatible complex structure on a plane field. This induces a almost complex structure on symplectization. Oh, I just remembered that some people have have strong opinions about which order this product should be written in. Is it the opposite order?
I don't know.
All right,
Fine. Got it, you.
with the usual contact form. And then we define differential depending on J from this algebra to itself. Using the usual kind of procedure by counting certain J hat holomorphic curves in SP. And particular curves we're interested in look like this. We have genus zero curves, several punctures, and the punctures consist of single ray orbit on top and possibly several ray orbits on bottom. And an important caveat is that we have to do the counting virtually. The well-known transversality issues with contact homology. And so we follow the construction of John Pardon. And for the most part, it doesn't really matter which virtual perturbation framework you use, but at some points we have to kind of open the black box a little bit. So this is what we use, and in particular, the differential depends not only on the choice of J, but also on so-called perturbation data. Okay, and then finally, the contact homology algebra. See over there. Is so now it depends on alpha J and theta. And this is the homology of this. Okay, so hopefully it's right in there. Oh yeah, and then, okay, one last thing is that one has to show that it's independent, that you get canonical isomorphisms between these invariants for different choices of the alpha, J, and theta. Okay, so what goes wrong for V open? It's the relevant compactness students for the modular spaces. So-called SFT compactness theorem, which is a much more general thing, but and the problem is that holomorphic curves can run off to horizontal infinity. So the picture looks like this. That inside our symplectization, we have the usual symplectization coordinate, and then additionally this t coordinate on our convex end. And you could have some horrible, okay, I'll call this the directions plus infinity and minus infinity. So I'll just call infinity. And you could have a sequence of holomorphic curves, say that are going further and further out. And then they wouldn't have a convergent subsequence in the modular space. Where's this one first? Okay, but the point, of course, is that we can recover this. We can recover the compactness in the convex case. So the recipe for defining the thing that we want to define convex is the following. So first, we'll define a certain class of contact forms and almost complex structures that we want to admit. And it'll depend on the convex structure. This is to be compared to the definition of symplectic homology when you consider certain admissible Hamiltonians and almost complex structures. So then we show that we can produce this invariant in the usual way, as long as we can restrict to the admissible ones. And this amounts to proving the appropriate compactness result in this case. Then we show that this is independent of the choice of alpha and j, but still for fixed convex structure. So this is this allows us to define an invariant just of the contact manifold with this convex structure. And this is also to be compared with symplectic homology in that there you normally take some limit over the various admissible pairs to get the invariant, whereas here it so turns out that you actually get an isomorphic thing for any choice of admissible one whatsoever. And so this is ultimately, it also follows from the appropriate compactness theorem, namely in the usual, you obtain the isomorphisms in the usual way by counting holomorphic curves in certain cobordisms, and it turns out that there we can produce the same compactness argument, and so we get the morphisms in the usual way. However, when you have different convex structures, then that argument doesn't work. So you have to do something else. So we use kind of an interpolation argument so that you can interpolate between different convex structures.
So in the end, you don't have to like take some colimit with respect to the convex structures. It's actually independent.
Right. Yeah. Here too, it turns out that any convex structure can take rule.
I see.
As it turns out, there is a colimit involved, but not like that.
Okay.
Okay. So I'm predictably running out of time faster than I intended. So let me just try to say something brief about admissibility. So let's fix contact manifold, contact form, and a convex structure and a oh, I see. Okay, sorry. See, okay, actually. Fix a contact manifold and a convex structure. And okay, I'll give the definition of J being immiscible because it's very simple. So, okay, first of all, we, as usual, only want to. Okay, saying things kind of out of order here, but assuming that we had fixed an alpha, we want to consider J's, which are the alpha compatible, as usual. J is admissible. Here, the only condition is that J be T invariant on the end. Okay, so we're always having this end picture in mind. It's not on the board anywhere. And you have a cylindrical end, so you know what it means for J to be T invariant, and that's what we meant. For alpha, which again, as usual, we demand that it be non-degenerate, is admissible. So there's two parts to the definition. First is the same kind of thing, an invariance on the end, although we can't quite demand that it be actually T invariant, but we demand at least that it converges as T goes to infinity. So converges. So I look at this chunk on the infinite end from T to T plus L. Those are all isomorphic because the cylindricality. And it converges to a contact form on. So these are all isomorphic too. To sigma times 0 as T0 goes to infinity. Okay, and then there's a second part.
Sorry, what does it say? So it says that the
all I'm saying is that when you look at the maybe I wrote something wrong, but when you look at the restrictions to various slices in the T direction, those restrictions that should converge to something. Okay, T infinity as T goes to infinity. So it's not T invariant, but it's asymptotically T invariant.
okay. So a T invariant contact form on that. I mean, I guess probably it has to be. Okay. So anyway, yeah, I understand. So
alpha isn't T invariant, but asymptotically it is.
sure, yeah, I get it.
I may have did I write something wrong?
No, I think we're good.
Okay, and the second condition is am I supposed to end in 10 minutes?
Yeah, but you have a couple more minutes, but
Wow.
I know.
I managed not to say anything. The second condition is that R alpha is nice. The Rig vector field should. So to formulate this, you need to say something about the geometry of convex hypersurfaces. But for those who know about it, they have a dividing set, a positive end, and a. Oh, sorry. This is so a dividing set, a positive end, and a positive part and a negative part, and the condition is that the Rig vector field should look like this. It should be outward pointing on the positive part, inward pointing on the negative part, and transverse. on the divided set. Okay, so the next thing I would like to do is describe the compactness argument. Maybe just to be able to say anything about it, can I eat into my
Go ahead.
Princeton a little bit? So briefly, the compactness argument runs as follows. So we argue by contradiction. So by the SFT, usual SFT compactness results, it's enough to show that all of the holomorphic curves we're interested in a given moduli space stay bounded within a compact set with respect to the base manifold. And so by contradiction, we suppose that there's a sequence of curves UN with say the image of UN intersects the set T is greater than N. So you have a sequence of curves going further and further out. And then we consider this, I have to say this very quickly because I don't have time. We partition the cylindrical end into these intervals, and n plus 1. Our condition on admissible forms guarantees that as you look at these restrictions, the restrictions of the contact forms converge to some contact form on the space which is diffeomorphic to each of these strips. And the idea of the argument is to say that the area of these holomorphic curves, by choosing the chunks appropriately, you can find a sequence whose areas are going to 0, which contradicts the but however, they're non-empty because they touch both sides, and this contradicts the fact that a holomorphic curve has positive area.
So you don't need to fix an energy bound in the curves.
We do. So
Okay.
yeah. So you first, so there's some subtleties involved. So first you have to fix one of these Helfer energy type contact forms. So and then we're looking at, say, curves with fixed asymptotics so that you get a energy bound.
So the compact set depends on this choice of energy bound.
Yeah. That's right. And so I'll just say one more thing about the argument, which is that supposing that all of these restrictions of the UNs remained inside of some vertically compact set like this, then you can just argue by the Gromov's monotonicity lemma to say that if you look at some ball, say in the middle, which they'll have to pass through, then the area inside that ball is going to 0, which is impossible. But if the curves are also escaping upwards at the same time, then we have to drag them all back down. And in doing so, we might inadvertently increase the symplectic area because our symplectic form is going to 0 at infinity. So there we instead argue using Fish's target local Gromov compactness theorem, which tells us that we can extract a subsequence inside this symplectic manifold with boundary, and then it ends by arguing that the limiting curve, so we get this convergent subsequence, we have a limiting curve say V, and it satisfies the d alpha is 0, this implies that the curve is cylindrical over a ray orbit, and we get a contradiction from that. Yeah, that's kind of outline of the argument, and I've already gone over time, so I'll stop there.
You got 5 more minutes if you want, but yeah, you can stop. You're welcome to stop. So maybe that's a good place.
Okay, well, yeah, I'll stop. If there aren't any questions, then maybe I'll say more. But
Okay, that's it. I have questions, so we could just stop and ask questions. Sure, sounds good. All right, thank you. I have some questions about this.
yeah, please.
So, okay, so you do this thing and then you, so then the result would be like something like a holomorphic curve with the ends on the two sides of the thing.
Yeah.
And I see, so it's not, so basically if it has 0 energy, it should be a cover of a ray orbit or something like that, or something.
Yes.
Inside of the cylinders over the characteristic affiliation, and it's just not because of this.
Yeah, it can't. So if it were, then it would have to kind of
Yeah.
go infinitely high, which it does not.
Yes.
That's where the contradiction comes from.
That makes sense.
Yes, I apologize to explain that so fast. Yep.
So why is, my two questions are, one, why is niceness useful for this whole argument?
Yeah.
And two, what's the flavor of the word interpolation?
Yeah. Good. Thank you for asking that. So the main result of the niceness is that all of the ray orbits of alpha happen before this starts happening. So niceness says that the ray vector field should look like this eventually, and you can see that out here there can't be any closed orbits. So all the ray orbits have to happen inside. That's the reason the niceness is useful, and specifically, yeah. So the interpolation is quite simple. So suppose we have two different contact forms which are admissible with respect to different convex structures. Then we look at an interpolated form which looks like alpha plus up to a certain point, and then has some mysterious behavior in between, and then eventually looks like some constant times alpha minus. And the other aspect, so there's one more condition on R alpha, which ensures that this is still an admissible contact form. It's now admissible not with respect to the alpha plus convex structure, but the alpha minus convex structure, because that's what it agrees with at the end. And moreover, you can see that alpha and alpha plus have the same ray orbits up to some action A. So really, you parameterize this whole construction by some action A, and by making it equal to alpha plus for longer and longer, you can ensure that it has all the same ray orbits of alpha plus up to that action. And the point then is that in order to compare say CH, I'll just write it as CH of alpha plus and CH of alpha minus. In order to compare these, which we can't do directly using a cobordism, because when you have two different convex structures, it's impossible to, you can't, it fails very badly, this argument. So instead, we just use that because they have the same ray orbits, and from a version of this argument, they have the exact same holomorphic curves. And so this is even isomorphic on the chain level to this CH of alpha A. But now this thing has the same convex structure at infinity as this one. So we do get a map like this. And then finally, we use that. Okay, so this is a usual action bounded version where you only look at orbits of action up to A. Then you use that the whole complex is a colimit of this. And with a little bit of effort, you can see that this map is independent of the choice of alpha A, and it commutes with all the inclusions in this directed system. So you get an induced map like that, and that's how you compare the different.
It was like in some.
Yeah.
Oh, I was just gonna say, so the punchline with the calculation ends up being, if I remember correctly, ends up being something like, if you delete a point and just use the standard convex structure, then it's actually the same as the closed case, right? Or something, is that what happens?
Yeah, so
So then,
so instead of removing a point, we take connected sum with Rn.
okay,
And when you take a connected sum, it by taking the neck thinner and thinner, you can ensure that up to any chosen degree, you're only introducing the only rate orbits you're introducing are the ones along the collar. And so you don't get so after you remove after you take this connected sum, you don't get the exact same contact homology as you had before. You get it. It turned out that the one before only had homology in even degrees, and now you add a bunch of homology in odd degrees. And it's a little bit subtle, but you can when you work the numbers out, you can see that it at least has to be non-trivial in some positive degree. Whereas the because Rn doesn't have any rate orbits, the contact homology for Rn is trivial. So that's enough to see that they're different.
I see, but it does do something to this, to remove a point and then convexify it like this.
Yes, yeah, it definitely does something.
Do you have any factorial properties of this version of contact homology?
Yeah, that's a good question. The answer is not really, although it's a very natural thing to try to work out, which I haven't done yet. But what we do have is, when we're proving the independence of the invariant for a fixed convex structure, then you can look at cobordisms between two contact manifolds which are isomorphic at infinity with the same convex structure. So for such cobordisms, you do get a punctoriality.
Okay.
But
Functoriality on the horizontal part, which is like if you have a V equivalent V prime.
I see, yeah.
It's not, I imagine.
Yeah, no, we haven't worked that out, but it's a very natural thing to.
All right, maybe we'll thank the speaker again and ask more questions after.